Humanity has lost over 75% of all languages ever spoken. Thousands of years of history, philosophy, and poetry have simply vanished as the physical records decayed. In 79 AD, Mount Vesuvius ended the silence of one Roman library by burying it. A wall of superheated ash and gas reached Herculaneum, instantly encasing a seaside villa in 500-degree heat. Today, those ruins sit quietly in the shadow of the volcano. Hidden within them was a vast collection of papyrus, the ancient world's greatest library. When the intense heat hit the papyrus, the scrolls didn't burn to ash. Instead, they carbonized, turning into fragile cylinders of charcoal. This flash baking perfectly preserved the text inside, but it fused the layers together. The result was a set of scrolls that looked exactly like lumps of coal, preserved but physically impossible to open. For 275 years after their discovery, these scrolls sat in museum vaults. They were an archaeological taunt, the wisdom of the ancient world held in a form no one could touch. Early attempts to physically peel back the layers were disastrous. Because the carbonized papyrus was so brittle, any human touch caused the material to crumble into dust. In 2023, computer scientist Brent Seales shifted the strategy. He launched the Vesuvius Challenge, releasing high-resolution digital X-ray scans of the scrolls and inviting the global programming community to find a way to read them. The challenge was to find a digital path through the charcoal. We needed to read the interior of a document without ever physically touching the page. The primary obstacle was the ink. Because ancient scribes used a carbon-based ink, it looks identical to the carbonized papyrus it sits on. To a human looking at a scan, the letters are invisible. However, there is a microscopic physical difference. The ink has a slightly different density than the burnt paper beneath it.
Researchers used high-energy X-ray CT scanning to create a 3D density map, pinpointing exact locations of microscopic ink particles. Then, AI virtually unwrapped and flattened the layers into a 2D sheet. Finally, neural networks scanned this surface, connecting dense particles to reconstruct characters. This process moved the struggle of archaeology out of the physical lab and into the realm of digital data analysis. The first success came from a 21-year-old student who ran a model that identified a single Greek word, porphyras, meaning purple. It was the first time a human had read a word from an unopened scroll in 2,000 years. By February 2024, a team of researchers had expanded that technique to decode 2,000 characters across 4 full columns of text. The recovered text revealed a previously lost work by the Epicurean philosopher Philodemus, who was writing about the nature of human pleasure and the senses. Digital unwrapping achieved in months what centuries of physical restoration could not. It proved that these charcoal blocks could be read as clearly as a modern book. Burnt scrolls are a specialized problem, but a much larger challenge exists across the Mediterranean. Thousands of inscriptions that are readable but physically shattered, with centuries of weather and war leaving massive gaps in the history. Google DeepMind developed the Ithaca and Aeneas models to solve this. These neural networks analyze the context of surviving fragments to predict missing words in ancient Greek and Latin stones. This chart shows the impact of that collaboration. Human historians working alone achieve about 25% accuracy in restoring these texts. When they work with the Ithaca AI, that accuracy jumps to 72%. These models amplify human expertise by providing a parallel search capability that no historian could achieve alone, cross-referencing thousands of existing texts to find the most likely match for a missing fragment. The same tools are now being used globally. In China, AI is filling in missing characters on 3,000-year-old oracle bonds, connecting symbols that were lost to time. Natural language processing is now being applied to the glyph blocks of the Maya, helping researchers parse complex grammar related to ritual and astronomy. Perhaps most importantly, AI is finding structural patterns in scripts that have never been decoded, such as the Minoan linear A, identifying sign families that suggest the presence of grammar. DeepMind's Yannis Asayel compares this to the invention of the telescope. It is a tool that allows historians to see further into the past, extending the reach of historical science. By cross-referencing known and unknown scripts at a superhuman scale, machine learning is providing the resolution we need to finally hear civilizations that have been silent for millennia. Scientists estimate that over the course of human history, we have spoken roughly 30,000 distinct languages. Today, roughly 7,000 survive. The rest, more than 75%, are gone, permanently. Many of these vanished cultures left behind physical records of their existence, writing systems carved into stone, stamped on clay, and pressed into tablets. Among those surviving fragments are the scripts of massive ancient empires. Despite decades of effort, linguists have never been able to read them. These unsolved scripts represent the trapped voices and obscured histories of entire societies. 5,000 years ago, the Indus Valley civilization stretched across modern-day Pakistan and northwest India, covering an area larger than ancient Egypt and Mesopotamia combined. The Harappan people were highly organized, but their script remains a mystery, appearing on approximately 4,000 surviving inscriptions on seals and pottery. Most texts are incredibly brief, averaging only 4.5 signs long, providing very little data for analysis. The second major barrier is the complete absence of a bilingual translation text. We have no Harappan equivalent to the Rosetta Stone to serve as a comparative reference. Without a direct linguistic bridge, human linguists are limited. The human brain cannot easily hold and cross-reference thousands of disconnected symbols to identify macro patterns. This is where artificial intelligence takes over. In this context, machine learning does not act as a direct translator. It operates as an engine for extreme pattern recognition. The methodology is already proven. In the Vesuvius challenge, machine learning successfully decoded carbonized Roman scrolls that were physically impossible for humans to read. DeepMind's neural network, Ithaca, analyzes damaged ancient Greek inscriptions to restore missing characters. With historians, their restoration accuracy jumps to 72%. The ability for AI to decode ancient text is an active capability currently rewriting classical history. Now, researchers are deploying these exact tools against the Indus script, starting with convolutional neural networks. A neural network processes the visual chaos of the 4,000 inscriptions, comparing every sign instantly to find visual similarities. Through this clustering, the AI successfully consolidated 417 distinct signs down to about 50 core grammatical units. Once those core units are defined, researchers apply a second tool, probability modeling. Using Markov chains, the software calculates the exact mathematical likelihood of which symbol will follow another in a sequence. This identifies the internal rules of the language. It reveals a strict grammar, even before we can assign meaning to the words. By combining clustering and probability, AI is mathematically cornering the script, bypassing the immediate need for a bilingual text. We see a related technique being applied to the maritime civilization of ancient Minoan Crete. 3,800 years ago, the Minoans wrote in a script we call Linear A. It remains entirely undeciphered. Today, AI tackles this using transfer learning. By training on the structural laws of its decoded successor, Linear B, AI can apply those patterns backward to the unknown script. This methodology leverages the structural skeleton of known civilizations to narrow the possibilities of unknown ones, turning guesswork into testable data. However, even machine learning has its limits. While AI can map grammar and cluster symbols, it cannot generate phonetic meaning without a factual anchor. Assigning definitive phonetic values still requires a human element, an archaeological excavation that finally uncovers a bilingual text. AI builds the map, but traditional archaeology must still make the physical discovery. For India, a decipherment breakthrough would be monumental. A decoded script would reveal the Harappans' connection to modern Dravidian speakers, their influence on Sanskrit, and their link to the Vedic age. This pursuit is an active, high-stakes investigation into the origins of South Asian identity. The ancient world was never truly silent. It was just waiting for humanity to build a machine smart enough to hear it.